Alright guys, so let's try this out. This is 7-4 number 37, the Lighthouse Problem. And our class is going to be starting here in about 5 minutes. So I'm going to kind of go through this question quickly so that it's not interrupted. What's going on here is there's this lighthouse that's right here in the center, and it's emanating light from both sides as it spins around and around, and this light is shining and it's touching the beach. And as the angle theta changes, this light, you can imagine what's going to happen with this point of light. It goes up the beach, and then when this ray of light down here comes on this side, it's going to be going up the beach in this direction. So y is the displacement in y measured from the point on the beach that is closest to the lighthouse. So this point right here all the way up here to y. And that's a lot of information. So I just threw together a GeoGebra picture for you. Here's our lighthouse. Here's the rays coming out both sides, and so you can track the ray of light traveling right here along the beach. If I could do one better, I can give that a point right here, so you can see that point traveling along the beach. The displacement y is this line from the closest point on the beach to the point where the light is touching the beach. So you can kind of see it as it travels up along here. And I've already kind of given away this situation. I meant to click off this, but if you watch closely here, you can tell we're trying to find y. We're trying to figure out what is this displacement y, and look at this word that's traveling right here. I meant to click off that. I don't want you to see that quite so soon. But yeah, you can see right here that this displacement, as they call it in the Lighthouse Problem, is the tangent line. The tangent line to what circle, you may ask? Well, the tangent line to that circle. So we have a circle with a radius of 500, and essentially what's going on right here is this displacement line is the line that travels along the tangent line as our angles get bigger and smaller. So what function models this behavior? I forget the exact wording that they say in the problem here. What function models this behavior? Write an equation for y in terms of theta. Well, you guys can see that the y in terms of theta is tangent of theta. It's going to be tangent of theta. So we can answer A then pretty quickly. And of course, I was so busy getting my other stuff together that I didn't cue my pen. So write an equation of y in terms of theta. Well, that displacement y will be in terms of tangent of theta. The only thing that we need to change here is, of course, the amplitude of tangent, right here, the implied amplitude is 1, because 1 times tangent theta. But you guys can see from here, this tangent line, this whole circle, is expanded, or it's dilated by 500. You can see the radius is dilated by 500. So the only thing that we would need to do to check this is put out in front of the tangent function a little 500. So there's our equation. Y is equal to 500 tangent theta. And you can see that that will give us this displacement from the closest point on the shoreline, which is the point of tangency right here. Whoop. All right, question B says, now let's imagine that this thing is traveling at an angular velocity of 5 degrees per second. So that's talking about our angular velocity. So this is going to mean that we have a period change. We have a frequency, an angular frequency change. Well, in order to do this problem, let's just kind of map this out right here. If theta is then in terms of seconds, so we take theta and we'll just call this t in terms of seconds. So 5 degrees, I think it says it's 5 degrees per second. And so if theta is t in terms of seconds, and we set up a little table here, well, when t is 1 second, how many degrees will have gone by? Well, if it's 5 degrees per 1 second, when 1 second goes by, then will have traveled 5 degrees. 2 seconds, 10 degrees. 3 seconds, 15 degrees, and so on and so on. And so you guys can maybe get the point now that the way you get theta is by taking the number of time, t in seconds, and multiplying it by 5. So the answer to B, and I'll label these. So this was A. The answer to B is our same function. Y is equal to 500 tangent. But since we know this lighthouse is traveling at 5 degrees per second, our angle will be measured as 5t. So every second that goes by, we'll go 5 degrees for our angles. Okay, very good. C. Now we know that there is a house on the beach with a displacement of positive 600 yards. Find the first 4 positive values. Okay, so let's go back to our graph here. So you can see right here what this is telling us then is that there is a house. I gotta scroll out to see it, zoom out. Oh, there it is. There is a house at positive 600 yards displacement from the nearest point. So what we're trying to find then is the first 4 times that this line stop will hit the house. So that's 1. Wait for it. Here comes again. All right, let's speed this up. 2. Keep going. 3 and 4. You get the point. So we're trying to figure out for what angles the smallest 4 angles where that point is going to hit the house. And we know the house is 600 yards displacement. So this y is our displacement. So then we can solve the equation 600 is equal to 500 tangent of 5t. So let's do a little bit of simplification here. Divide both sides by 500 and simplify. So 6/5 is equal to tangent of 5t. Take the inverse tangent of both sides, and so we're going to have inverse tangent of 6/5 plus the period, because we know it's going to be rotating. We know that the tangent function repeats every pi. See how one light is pi distance away from the other light? So we know that the period of tangent is always pi. You can see it here. So instead of plus 2 pi, we say plus pi n, where n's an integer, is equal to 5t. And our last step here is divide both sides by 5. So I'll distribute 1/5 to both those terms. So 1/5 inverse tangent of 6/5 plus, oh geez, I used pi, didn't I? We're talking about this in terms of degrees. So pi radians is the equivalent to 180 degrees divided by 5n, and that's going to give us our t. So we have 1/5 inverse tangent of 6/5 plus 180 divided by 5 is 36. 36n is going to be RT. So now we just have to do that for the soonest 4 times. The soonest 4 times. So let's take when n is equal to 0 and plug that into your calculator. So 36 times 0 is just 0. So it'll just be that 1/5 inverse tangent of 6/5. And I did this already. Just getting ready. And I think it was 10.039 seconds when n was equal to 1. So you just add 36 seconds on, or add 36 onto this, because plus 36 would be the period. And that would be 46.039. And then back around again. So not to the original point, but on the one diametrically opposite of it. Pi radian shifted over, 180 degrees shifted over. So back around again, add another 36. And I got 82.039. And then our last one, our last rotation, add another 36, and we are at 118.039 seconds. So those are our 4 solutions. I hope this diagram helped you out and helped you to realize that this is just the tangent function over and over and over again. There you go.